This part will talk about the process of spirometry and the measurement of different lung volumes and lung capacities. What you're seeing here is a spirometer. You see a patient hooked up to a spirometer where there is a nose clip to make sure that we're capturing the passage of air through the oral cavity and that none of the air is getting in or out through the nose. And then we ask the patient to use the mouthpiece and either inhale or exhale, and recording the passage of air or the airflow is recorded, and you can either see it on the computer screen or print it out if needed. Again, that process is known as spirometry, and the apparatus used is the spirometer. Now, what are the different lung volumes and lung capacities? So we'll break them down into one at a time. Don't worry about the actual milliliters and liters and like the values of them, but you do want to make sure that you're comfortable with the names and the definitions of them. So the first and the easiest one is the tidal volume. When you ask the patient to just breathe in and out normally at rest, it gives you this wave of air going in and out of the lung, and that is known as the tidal volume. So again, the tidal volume is the passage of air or the flow of air in and out at rest. The inspiratory reserve volume, you would ask the patient to take a normal breath, and then after that normal inhalation, you ask the patient to inhale as maximal as possible. Okay, so normal breath in, and then maximal inhalation. That is known as the inspiratory reserve volume. So the inspiratory reserve volume is the maximal amount of air that can be inhaled after a normal inhalation. Compare that to the expiratory reserve volume. So again, you ask the patient to exhale normally and then to push air out of the lungs as much as possible. So a normal exhalation followed by a maximal exhalation. That, again, is the expiratory reserve volume, which is the maximal amount of air exhaled out of the lung after a normal exhalation. Whatever remains in the lungs after maximal exhalation is known as the residual volume. So no matter how much you try to exhale and try to empty the lungs are going to, there will always be some air left in the lungs, and that's why the lungs don't collapse. And that amount of air left in the lungs after a maximal exhalation is known as the residual volume. Now know that using all of these volumes, the spirometer can measure the tidal volume, inspiratory volume, and expiratory reserve volume, but it cannot measure the residual volume. So in order to measure the air, the air has to flow through the spirometer. And since the residual volume always remains inside of the lungs, it's not passing through the machine. That's why the machine cannot pick it up. So again, the spirometer has the ability to measure the tidal volume, inspiratory reserve, and expiratory reserve volumes, but not the residual volume. Now for these capacities, you'll find that capacities are made out of two or more volumes added up together. So the vital capacity is equal to the inspiratory reserve plus the tidal volume plus the expiratory reserve volume. So all three of those volumes together make the vital capacity. And the vital capacity is one of, if not the most important of all of these capacities that we use in order to diagnose diseases and check on the progress of diseases. So the vital capacity would be, you ask the patient to inhale as much as possible and then exhale. You want to think of it kind of like taking a deep breath in and then blowing out candles. Okay, so deep breath in, then you blow out the candles, and you keep on blowing as hard as possible. So again, inspiratory reserve plus tidal volume plus the expiratory reserve volume. 3 of those together would make up your vital capacity, and that again is what we use to diagnose and to track the progress of patients, respiratory patients. Now the functional, so to define the vital capacity, in scientific definition, it would be the maximal amount of air exhaled after a maximal inhalation. Now to the functional residual capacity, which it equals the expiratory reserve plus the residual volume. By definition, that would be the amount of air left in the lung after a normal exhalation. So after a normal breath out, whatever is left in the lungs, that would be the functional residual capacity. And again, it's equal to the expiratory reserve plus the residual volume. Next would be the inspiratory capacity, and that would be the maximal amount of air inhaled after a normal exhalation. So after a breath out, you ask the patient to inhale as much as possible. That would include the tidal volume plus the inspiratory reserve. So that would be the inspiratory capacity. Now the total lung capacity would be adding up all of these different volumes. So the inspiratory reserve plus the tidal volume plus the expiratory reserve and the residual volume. So the total lung capacity would be the amount of air found in the lungs after a maximal inhalation. So you inhale as much as possible. Now, whatever amount of air found in your lungs at that time, that is the total lung capacity. From one person to another, depending on health and gender and so on and age, but on average, it is about 5 to 6 liters of air. Now, these are the definitions. Again, for the values, don't want to worry about those, but you want to make sure that you're good with the definitions. Now, when we inhale, that tidal volume, which was half a liter, okay, so 500 milliliters, which again would be the amount of air that we inhale at rest and exhale at rest. Not all of that air reaches the alveoli. Part of it remains stuck in what is known as the anatomical dead space. So a dead space means that is an area in the respiratory tract where there is no exchange of gas, which basically means it's in the conducting airways. So out of that tidal volume, 350 will get into the alveoli, and the remaining 150 milliliters remains in the anatomical dead space. Now come the next breath, the next tidal volume coming in. Now we'll push that 150 back in, plus the 350, so now we have a total of 500 in the alveoli available for gas exchange, while the remaining 150 of that second breath, again, remains stuck in the conducting pathways, and those, again, would be considered the anatomical dead space, which is a normal finding. So the anatomical dead space of 150 milliliters is normal range. And this ends this part.